Example 10.2 A. When monochromatic light is incident on the surface separating two media, the reflected and refracted light both have the same frequency as the incident frequency. Explain why. So, during the refraction or reflection, when the light wave interact with the constituent particle of the matter, એટલે atom ની એની સાથે જ્યારે interact કરે, so at that time those constituent particles also oscillate with the frequency exactly equal to frequency of the light, and therefore the frequency of light that remains constant if the medium is changed. Now B. When light travels from a rarer to denser medium, the speed decreases. Does the reduction in the speed imply the reduction in the energy carried by the light wave? No. When we consider the wave nature of light, then the energy that depends on the square of amplitude. Okay, it does not depend on the velocity. Then C. If the wave picture of light, intensity of light is determined by the square of the amplitude of the wave, what determines the intensity of light in the photon picture of light? So in the photon picture of light, the number of photons incidenting or crossing per unit area, that give you the intensity of light. આપણે ડ્યુઅલ નેચર વાળા ચેપ્ટરની અંદર આ વસ્તુ ભણી ગયેલા છીએ. ઓકે, ક્લિયર ટુ ઓલ ઓફ યુ? Next topic, that is coherent and incoherent addition of waves. Now actually here we have to discuss the phenomenon named as interference. So first of all, we have to understand what is interference. Interference means what? So the effect produced by superposition of two or more than two waves, that is called interference. The effect produced by the superposition of two or more than two waves, that is called interference. Now, interference can be obtained only if the sources from which the waves are emitted, those two sources are coherent sources. If sources are incoherent sources, then you will not get the interference. But now coherent sources means what? The sources for which the phase of the oscillations of the wave that either remains constant or it is same one. So for the coherent sources, when the waves are produced and those waves superpose at any point, there the phase difference for superposing waves, that will be either zero or it will remain constant. So these type of sources are known as coherent sources. And to get the interference, the basic requirement, that is of coherent sources. For incoherent sources, the phase for the oscillations of the wave produced from the sources, that will not remain constant. It is continuously changing with time. So are known as incoherent sources. તો હવે કોહેરન્ટ સોર્સિસમાંથી જે વેવ્સ જનરેટ થશે એ કોહેરન્ટ વેવ્સ થશે, અને ઇનકોહેરન્ટ સોર્સિસમાંથી જે વેવ્સ જનરેટ થશે will be incoherent waves. Okay, now we know the superposition principle. When any particle is oscillating under the effect of superposition of two or more than two waves, then its displacement will be equal to the vector summation of the displacements under the effect of individual waves. એટલે coherent sources માંથી જે coherent waves પ્રોડ્યુસ થયા અને એ કોઈ પોઈન્ટ પાસે સુપરપોઝ થતા હોય તો ત્યાં જે પાર્ટિકલ હોય એ પાર્ટિકલનું ડિસ્પ્લેસમેન્ટ એ જે વેવ્સ ત્યાં સુપરપોઝ થાય છે એ દરેક ઇન્ડિવિજ્યુઅલ વેવના લીધે જે ડિસ્પ્લેસમેન્ટ થાય એના સમીશન જેટલું આપણે લેતા હોઈએ છીએ. ઓકે, so now let's first consider the addition of coherent waves. Suppose here we have two coherent sources S1 and S2, and here on the screen placed against it, the point P is on the normal bisector of the line joining to this S1 and S2. એટલે S1 S2 ને join કરીએ તો એના ઉપર જે નોર્મલ બાયસેક્ટર આપણે અહીંથી તૈયાર કરીએ લાઈન ઉપરથી અને એ સ્ક્રીન ઉપર જ્યાં આપણને આ પોઈન્ટ આપે એ પોઈન્ટ P છે. તો obviously S1P that will be equal to S2P. Okay. Now on the screen at any point for any particle, okay, the displacement that will be equal to the summation of the displacements under the effect of individual wave. Suppose displacement of the particle at point P under the effect of the wave produced by source S1, that is y1 equal to a cos omega t. કારણ કે સિમ્પલ હાર્મોનિક મોશન કરશે તો એનું ડિસ્પ્લેસમેન્ટ આપણે સ્ટાન્ડર્ડ 11th માં ભણી ગયા છીએ, રાઈટ? આપણે ઇનિશિયલ ફેઝ અહીંયા 0 લીધેલો છે એના ઓસિલેશન્સ માટે. So y1 equal to a cos omega t, and here the intensity of the wave at point P I0 that proportional to a square. Okay. હવે displacement of the particle at point P due to the wave produced from the source S2. Suppose it is y2 equal to a cos omega t. Here also the intensity proportional to a square. So now, due to superposition of these two waves at P, the resultant displacement at P, that is given by y equal to y1 plus y2. So a cos omega t plus a cos omega t. So resultantly you can write y that is 2a cos omega t. Now intensity proportional to the square of amplitude. It implies that here you will get the resultant intensity proportional to 4a square. Now the maximum intensity at point P when cos omega t that is 1, so that will be equal to 4I0. A square is replaced by I0. So when at a point due to superposition of the waves we get maximum intensity, then we say this thing, at that point constructive interference takes place. Constructive interference takes place at that particular position. Clear to all of you? So experimentally when we get the interference pattern at that time, we can observe this thing. At point P we get the bright fringe with maximum intensity 4I0. It implies that at point P, the constructive interference is obtained. Okay. Now, After that, at point Q also, we will get the constructive interference. It implies that at point P or Q also we get the bright fringe. Okay? તો હવે આ Q point જે છે એ આપણે માનો કે એ ટાઈપનું છે કે when we consider this point Q, then the path covered by the wave produced from source S1, that is S1Q, and the path covered by the wave produced from the source S2 to Q, that is S2Q. The path difference for these two waves when they superpose at point Q, that is, तो एक वेवे S2Q डिस्टन्स कवर કર્યું, બીજાએ S1Q, the path difference between these two, suppose it is equal to lambda. Suppose it is equal to lambda. હવે જો if we take the displacement produced by the wave from S1 at Q, that is Y1 equal to A cos omega t. Then displacement produced by the wave from S2 at Q, that will be how much? So we can write that will be Y2 equal to A cos omega t plus 2 pi. કારણ કે જો આપણે અહીંયા આગળ ફેઝ ડિફરન્સ 2 પાઈ નો એડ કરીએ તો જ આપણું ફાઇનલ ડિસ્પ્લેસમેન્ટ ઇક્વેશન Y2 equal to A cos omega t થાય. તો P પાસે સુપરપોઝિશન માટેની જે કન્ડિશન્સ હતી એ સેમ આપણને મળે. ક્લિયર? તો પછી તમે Y1 plus Y2 કરો એટલે ફરી પાછું આપણને રિઝલ્ટન્ટ ડિસ્પ્લેસમેન્ટનું ઇક્વેશન 2A cos omega t મળે અને આપણને મેક્સિમમ ઇન્ટેન્સિટી મળે. હવે જો એવી જ રીતના Q થી આગળ આપણે કોઈ R પોઈન્ટ લઈએ કે જ્યાં આપણને કન્સ્ટ્રક્ટિવ ઇન્ટરફેરન્સ એટલે અગેન મેક્સિમમ ઇન્ટેન્સિટી મળતી હોય, તો ત્યાં એક જ પોસિબિલિટી છે પાથ ડિફરન્સ માટે કે S2R minus S1R, that will be 2 lambda. Suppose we consider the displacement produced by the wave from S1, that is A cos omega t. Then Y2, that is we can take A cos omega t plus 4 pi. કારણ કે અહીંયા જો આપણે plus 4 pi નો phase difference લઈએ આ બે વચ્ચે, તો again the equation will remain same one, A cos omega t. So again the resultant displacement, that is 2A cos omega t, and you will get again the maximum same intensity. Clear? So here we can say now on the screen at any point the condition for constructive interference that we can write the path difference S1P minus S2P, that is n lambda, where n equal to 0, 1, 2, 3. So if we take n equal to 0, then path difference is 0, and here at point P we will get the constructive interference, means bright fringe. When we take n equal to 1, then the path difference at the point of superposition will be equal to lambda. એટલે આ Q point થયું, right? So we can say the condition for the constructive interference in terms of path difference, that is equal to n lambda. So we can say the point on the screen where the path difference between superposing waves, that is of the order of n lambda, there you will get constructive interference, and at those positions you will get the maximum intensity of the light, or we can say there we will get the bright fringe. Now see, suppose we take any point P for which the displacement due to the wave produced from S1, that is A cos omega t, and the displacement due to the wave produced from source S2, that is Y2 equal to A cos omega t plus phi. Okay. Now, practically, when we obtain the interference pattern, then in that we have bright, dark, bright, dark, bright, dark fringes. Dark fringes represent the zero intensity of the light. Now, intensity proportional to square of amplitude. So if the intensity is zero, means amplitude is zero, means displacement is zero. તો હવે સ્ક્રીન ઉપર આ બધા જે પોઈન્ટ છે કે જ્યાં ઇન્ટેન્સિટી ઝીરો મળે છે, તો ત્યાં રિઝલ્ટન્ટ ડિસ્પ્લેસમેન્ટ પણ ઝીરો હોય. હવે રિઝલ્ટન્ટ ડિસ્પ્લેસમેન્ટ આપણે લખીએ છીએ y ઇક્વલ ટુ y1 પ્લસ y2. હવે y1 આપણે a cos omega t લીધું, y2 that is a cos omega t plus 5. અને જો y1 plus y2 તમારે 0 જોઈતું હોય તો y2 જે છે એ માઇનસ a cos omega t થવું જોઈએ મેથેમેટિકલી. એનો મતલબ કે આ phi જે છે phase difference for these two, તો આ જે phi છે એ કેટલો હોય તો y2 માઇનસ a cos omega t થાય. તો મેથેમેટિક્સમાં તમે ભણી ગયા છો ટ્રીગોમાં કે if phi that is pi, 3 pi, 5 pi, 7 pi એવી કોઈ પણ વેલ્યુ હોય, then your y2 will be minus a cos omega t, and the resultant displacement of the particle at that point y1 plus y2 will be 0, then intensity will be 0. એટલે આપણે એવું લખી શકીએ કે phi that is 2n minus 1 into pi. ઓકે. હવે 2 pi રેડિયન ફેઝ ડિફરન્સ ને કોરસ્પોન્ડિંગ પાથ જે છે એ લેમ્બડા જેટલો હોય. તો હવે pi that is corresponding to lambda by 2 path difference. So S1p minus S2p, that will be 2n minus 1 lambda by 2. So here n equal to 1, 2, 3 and so on. Or you can write 2n plus 1 into lambda by 2, where n equal to 0, 1, 2 and so on. So now here we can say this thing. The points on the screen where for the superposing waves, if this particular condition in terms of path difference is satisfied, then we will get destructive interference at all those points. Destructive interference means intensity is 0 or resultant amplitude at those points that is 0. તો સ્ક્રીન ઉપર આપણે જ્યાં 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 બ્રાઇટ ફ્રિન્જીસ મળે ત્યાં એવું કહી શકીએ બ્લાઇન્ડલી કે path difference for the superposing waves that is of the order of n lambda. બરાબર. અને જ્યાં જ્યાં આપણને ડાર્ક ફ્રિન્જીસ મળે છે બધી પોઝિશન્સ પાસે આપણે કહી શકીએ the path difference for the superposing waves that is of the order of 2n plus 1 lambda by 2. જો આપણે n equal to અહીંયા 0 મૂકીએ, right? તો બ્રાઇટ ફ્રિન્જ આપણને સેન્ટરમાં મળે. પછી n equal to 1 લઈએ તો that is called first order constructive interference. પછી n equal to 2 લો તો that is second order constructive interference. એ જ રીતે અહીંયા આગળ 1, 2, 3 બરોબર છે. એ રીતે આપણને order મળશે બધા. ચાલો, clear? Any doubt in this one? Now suppose displacement of the particle at a point under the effect of the wave produced from source 1, that is y1 equal to a cos omega t, and the displacement of that particle under the effect of the wave produced from the source S2, that is a cos omega t plus 5. આ બે વેવ વચ્ચે ફેઝ ડિફરન્સ જે છે કેટલો છે આપણને ખબર નથી, એટલે ઇન જનરલ આપણે phi લખી નાખ્યું. ઓકે, હવે જો resultant displacement that will be y equal to y1 plus y2. So y, that is a cos omega t plus a cos omega t plus 5. Take a common. So cos omega t plus cos omega t plus 5. So cos plus cos. For that resultantly we can prepare the equation 2a cos 5 by 2 into cos omega t plus 5 by 2. તો હવે cos omega t plus something એનો મલ્ટીપલ જે છે જુઓ મેં અહીંયા સ્ક્વેર બ્રેકેટમાં લખ્યો, તો એ મલ્ટીપલ that will be the resultant amplitude. So we can write the resultant amplitude, that is 2a cos 5 by 2. So the resultant intensity at the point of superposition, which proportional to the square of amplitude, that we can give by equation I equal to 4a square cos square 5 by 2. હવે ઇન્ડિવિડ્યુઅલ વેવ માટે એમ્પ્લિટ્યુડ a હતો, મીન્સ કે એની ઇન્ટેન્સિટી પ્રોપોર્શનલ ટુ a સ્ક્વેર હોય. So we take that intensity, maximum intensity of the wave, that is I0, a individual wave ni. So here we can write the resultant intensity at the point of superposition of the waves, that is 4I0 cos square 5 by 2. Now the points where we get constructive interference, there the intensity will be maximum, and the points where we get the destructive interference on the screen, the intensity will be 0. તો હવે જો આ ઇક્વેશન ઉપરથી આપણને સમજ પડે કે maximum possible intensity, that is 4I0, ક્યારે મળે? When cos square 5 by 2, that is 1. Okay, so we can say for constructive interference intensity, that is 4I0, and that will be only when cos square 5 by 2, that is 1. So cos square 5 by 2, that will be equal to 1 only when 5 by 2, that is equal to 0, pi, 2 pi, 3 pi, and so on. Take these two on right hand side. So you will get phi, that is 2n pi, that is here n equal to 0, 1, 2, 3, and so on. So here see phi, that is 2n pi. A phi જે છે આ બે વચ્ચેનો phase difference છે. It implies that we can say this thing, this is the condition for constructive interference in terms of phase difference between superposing waves. હવે simple, 2 pi radian phase difference, that is equivalent to the path difference of lambda. તો હવે 2 pi ની જગ્યાએ આપણે lambda substitute કરીએ, તો path difference, that is of the order of n lambda, where n equal to 0, 1, 2, 3, and so on. So path difference equal to n lambda, then we can say this is the condition for constructive interference in terms of path difference between superposing waves. કેટલું simply આવી ગયું. Now conditions for destructive interference, we know when the destructive interference takes place at any position, the resultant intensity, that is equal to 0. So in the equation you can understand the resultant intensity will be 0 when cos square 5 by 2, this particular term, that is 0, because 4I0, that is constant one. So when cos square 5 by 2, that is equal to 0, then I will be 0. So pi by 2, if it is pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on, then and then only cos square phi by 2 will be 0. So 2 will be cancelled from both sides. So we can write phi, that is pi, 3 pi, 5 pi, and so on. So phi, that is equal to 2n plus 1 into pi, where n equal to this one. So now we can say this one is the condition for destructive interference in terms of phase difference between superposing waves. Or we can say, in other words, on the screen, at those points where for the superposing waves, the phase difference is of the order of 2n plus 1 pi, there we will get a destructive interference. Now, 2 pi phase difference corresponds to path difference equal to lambda. So for pi, we can write lambda by 2. So path difference that will be of the order of 2n plus 1 lambda by 2. It implies that this is the condition for destructive interference in terms of path difference between superposing waves. So we can say, now in terms of path difference, we can say this thing, at all those points on the screen where the path difference between superposing waves that is of the order of 2n plus 1 lambda by 2, there we will get the destructive interference. Clear to all of you? Incoherent sources. Now, for incoherent sources, the phase difference between the sources changes with time. Okay, so due to that, what happens? At the point of the superposition on the screen, we have to take now average intensity. So we have the equation for the intensity, that is I equal to 4I0 cos square phi by 2. So here we have to take average of it. So average intensity, that is average of 4I0 cos square phi by 2. 4I0, that is constant. So we can write 4I0 average of cos square phi by 2. But average of cos square phi by 2, that is 1 by 2. Maths વાળા જાણે છે કે cos square theta, that is 1 plus cos 2 theta by 2. Clear? અને પછી cos 2 theta જે છે એનું integration over 1 period 0 થઈ જાય, એટલે આન્સર 1 by 2 થાય. બાયોલોજી વાળા યાદ રાખજો, right? So we will get the average intensity at the point of superposition, that is 2I0. એટલે જેટલા સોર્સિસ હોય એ દરેકે દરેક સોર્સની જે ઇન્ટેન્સિટી હોય એનું સિમ્પલ સમેશન થાય એટલી રિઝલ્ટન્ટ ઇન્ટેન્સિટી એટ ધ પોઈન્ટ ઓફ સુપરપોઝિશન આપણને મળે. Clear to all of you? Now next, that is interference of light waves and Young's experiment. Very first scientist, Thomas Young, derived the interference pattern. He observed the interference pattern. Now, the basic requirement to get the interference pattern, that is the coherent sources. And any two different sources can't be coherent sources. એટલે થોમસ યંગે શું કર્યું હતું કે સોર્સ એક જ લીધો અને એને બે પાર્ટમાં ડિવાઈડ કરી દીધો. When he obtained the interference pattern, at that time he took sunlight as a source. He took one cardboard, on it one pinhole was made. and sunlight was passed through it. So now from this side, when we observe that particular pinhole, then we can say when the sunlight is coming out from that pinhole, means that pinhole is now a source of light. Then parallel to it, another cardboard was taken on which two very close pinholes were prepared, and the sunlight coming out from this single pinhole, this one, was passed through these two pinholes. So when the light comes out from these two pinholes, then we can say these two pinholes will now behave as two sources. And now the light waves coming out from these two pinholes, when superposed on the screen, you will get the interference pattern. So in this way, very first scientist Young observed the interference pattern. Okay. Now see, this is known as Young's double slit experiment. Okay. So here, now in this next theory, we have to discuss the position of the fringe on the screen. Now see, suppose we have two sources S1 and S2 which are separated by the small distance small d, and these two sources are coherent sources, and against these two sources the screen is placed at distance capital D. Point O on the screen, that is on the normal bisector of the line joining to these two sources. So we can say this portion is d by 2, this one is also d by 2. Now consider the superposition of the waves from S1 and S2 at any arbitrary point P on the screen, which one is situated at a distance x from the point O. Okay, so we can say the path difference for the waves superposing at point P coming from source S1 and S2, that is given by S2P minus S1P. હવે જો આપણે S1 અને S2 માંથી આપણે સ્ક્રીન ઉપર નોર્મલ ડ્રો કરીએ, which are Q and Q dash. ઓકે, હવે આપણે S2P અને S1P નો જે ટર્મ્સમાં પાથ ડિફરન્સ અહીં લખ્યો એ ફાઇન્ડ આઉટ કરીએ. ઓકે, હવે જુઓ S2P, this one. So here consider the triangle S2Q dash P. તો અહીંયા right angle triangle થયો. તો એના માટે તમે લખી શકો કે S2P square that is equal to S2Q dash square plus Q dash P square. હવે જો S2Q dash that is capital D, એટલે મેં ડાયરેક્ટ લખ્યું છે that is D square, અને Q dash P, તો O2P that is X and O2Q dash that is equal to this D by 2. So resultantly we can write Q dash P square that is X plus D by 2 whole square. Similarly, to find out S1P, here see, take the triangle S1QP. So at Q it is right angle. Now we can write S1P square that is S1Q square that is D square plus QP square. So we can write QP that is this X minus D by 2. Okay. So S1 P square, that is D square plus X minus D by 2 whole square. Now take S2 P square minus S1 P square. Take the difference of these two equations. So D square plus X plus D by 2 whole square minus D square plus X minus D by 2 whole square. Now simplify this one, D square plus this one, X square plus XD plus D square by 4. This is second bracket, minus D square minus X square plus XD minus D square by 4. So D square, X square, and D square by 4 cancelled. So we can write S1P square minus, S2P square minus S1P square, that is equal to 2XD. But on left hand side, we can simplify this one as per A square minus B square, that is A minus B into A plus B, like that. We can write S2P minus S1P into S2P plus S1P, and that is equal to 2XD. So S2P minus S1P, that is 2XD upon S2P plus S1P. But here, say, the separation between these two sources, that is very less compared to D. Normally, S1, S2 આ જે ડિસ્ટન્સ સ્મોલ d છે એ મિલીમીટરથી શરૂ કરી અને 1/10 ઓફ મિલીમીટરના ઓર્ડરમાં હોય, એટલું ઓછું હોય. અને source or slit to screen, capital D, એ 50 સેન્ટીમીટર to 1 મીટરના ઓર્ડરમાં હોય, એટલે 50 સેન્ટીમીટર to 100 સેન્ટીમીટર. So when D that is very much greater than small d, then here we can take the approximation, that is S2P nearly equal to capital D and S1P that is nearly equal to D. એનું સમેશન લેવાનું છે એટલે લઈ શકીએ આપણે, right? So resultantly this S2P plus S1P you can write 2D, 2 cancel. So S2P minus S1P, that is XD by D. But S2P minus S1P, that is called path difference, right? એટલે આ આપણને path difference નું equation મળી ગયું, where X that is the position of the point on the screen. એટલે હવે જો આપણે શું કહી શકીએ કે if the path difference at the point of the superposition, which is XD by D, where X is the position of the point, that is of the order of n lambda, then there we will get constructive interference. Means X equal to n lambda D by D. તો હવે જુઓ, X that is the position of the point, એટલે screen ઉપર starting from O at distances n lambda by D, એટલે કે lambda by D, 2 lambda by D, 3 lambda by D, 4 lambda by D, આ બધા જ distances ઉપર આપણે constructive interference મેળવીશું, and at all those positions we will get bright fringe. હવે destructive interference માટે આપણે condition લઈ આવ્યા હતા કે path difference, but path difference that is XD by D. So if it is of the order of 2n plus 1 lambda by 2 at the point of superposition, then there we will get the destructive interference. એટલે હવે જો અહીંયા આપણે x ને સબ્જેક્ટ કરીએ, then 2n plus 1 by 2 lambda d by d, or we can write x equal to n plus 1 by 2 lambda d by d. It implies that starting from O at distance lambda d by 2d, then 3 by 2 lambda d by d, then 5 by 2 lambda d by d, then 7 by 2 lambda d by d, at all these positions we will get the destructive interference, and at all those points or the positions we will get dark bands on the screen. એટલે સ્ક્રીન ઉપર dark bright bands અથવા તો constructive interference કે destructive interference કયા ઓર્ડરનું એક્ઝેક્ટલી કઈ પોઝિશન ઉપર મળશે એ પણ આપણને આનાથી સમજ પડે. Clear to all of you? Now see here, suppose from S1 we draw normal on S2P, this one. Then here see, small d is very much less than capital D. So in that particular case, if we draw the normal from S1 to S2P, that is S1M, then we can say the path of the waves S1P and MP will be equal. So here we can say the path difference between the waves from S1 and S2, that we can give path difference that we can give by S2M also. Now see here, at S1, if this angle we consider theta, then this particular angle that will be also theta. Clear? So if you want to find S2M, then for that, if you take sine theta, this is for triangle, S1, M, S2, then we can write sine theta, that is opposite S2M, upon hypotenuse, that is S1, S2. So we can write therefore S2M, the path difference, that is equal to S1, S2 sine theta. Therefore, we can write path difference, that is S1, S2 is small d sine theta. So we can write now path difference, which one is given by xd by d, that is also given by d sine theta. Okay, clear to all of you? And now see here, suppose you take sine theta for triangle this one, then sine theta, that is opposite upon hypotenuse this one. But here theta is very small. So we can write sine theta, that is nearly equal to tan theta. So tan theta, that is x by d. So here you can write this is nearly equal to d tan theta, but tan theta from this another triangle, that you can write, that is x by capital D. It implies that you can write the equation of path difference in terms of sine theta also, in terms of tan theta also. Clear? એટલે તમને ક્યારેક path difference d sin theta ની ટર્મ્સમાં આપે કે d tan theta ની ટર્મ્સમાં આપે, તો બી વસ્તુ એ જ છે, ધ્યાન રાખવાનું તમારે. ક્લિયર એકદમ? સમજ પડી બધાને? The next topic, that is distance between consecutive bright or dark fringes. Now, Suppose we take the consecutive bright fringes. So for nth order bright fringe, we can write the position on the screen, that is xn equal to n lambda capital D by small d. We want consecutive. So now take n plus 1th order bright fringe. So it will be at the position xn plus 1, that is. Now here we have to write n plus 1 lambda capital D by small d. So distance between these two consecutive bright fringes, that is xn plus 1 minus xn, which is also denoted by x bar, or it is also denoted by beta. So that is n plus 1 lambda d by d minus n lambda d by d. So take lambda d by d common, you will get x bar or beta, that is n plus 1 minus n lambda d by d. So you will get x bar, that is beta, that is lambda d by d. Means the distance between consecutive bright fringes, that is lambda d by d. Similarly, if you think about dark fringes, then suppose here in first equation, you consider nth order dark fringe, then you have to consider the position xn, that is equal to n plus 1 by 2 lambda d by d. Then if you take n plus 1th order dark fringe here, then you have to write the position is xn plus 1. Now replace n by n plus 1. So resultantly you will get n plus 3 by 2 lambda d by d. And again take the difference of those two equations. Your answer will come to lambda d by d. It implies that if we take the distance between two consecutive dark fringes or bright fringes, that is the same one, lambda capital D by small d. It implies that in the interference pattern, all the fringes are with same width. અને આગળ ઉપર આપણે જોઈ ગયા કે interference pattern ની અંદર all the bright fringes are with the same intensity, that is 4I0, and all the dark bands or dark fringes are with the same intensity equal to 0. અને બધાની width પણ same હોય છે. એટલે જ distance between any two consecutive dark or bright fringes, that comes to same one. Clear to all of you? Now in the text, a simple photograph for the experimental arrangement. The slit source, single slit. Against it we place two slits, so your source will be divided in two parts, and on the screen we will get the fringes. Fringes no photograph આ type નો હોય. અને જો intensity માટેનો આપણે graph draw કરીએ, right? તો સેન્ટરમાં આપણને બ્રાઇટ મેક્સિમમ ઇન્ટેન્સિટી, પછી એની બાજુમાં ડાર્ક એટલે કે 0, પછી ફરી પાછી મેક્સિમમ એટલે પાથ ડિફરન્સ 1 લેમ્બડા 2 લેમ્બડા 3 લેમ્બડા, ત્યાં બધે આપણને મેક્સિમમ ઇન્ટેન્સિટી મળે. અને લેમ્બડા બાય 2 3 લેમ્બડા બાય 2 5 લેમ્બડા બાય 2 આ બધે આપણને ડાર્ક બેન્ડ્સ મળે. એટલે this is the photograph and intensity distribution curve for the interference pattern. Clear to all of you? Example 10.3. Two slits are made 1 millimeter apart and the screen is placed 1 meter away. What is the fringe separation when blue-green light of wavelength 500 nanometer is used? Very simple question. Lambda is given to you 500 nanometer, so that is 500 into 10 raised to minus 9 meter. So that is 5 into 10 raised to minus 7 meter. D, the distance between slit and screen, that is 1 meter. Small d, the separation between two slits, that is 10 raised to minus 3 meter, because it is 1 millimeter. Now fringe spacing, simple thing, lambda capital D by small d, substitute the values, you will get the answer. પણ હવે અહીંયા છે ને મેં આ એક એડિશનલ વસ્તુ મૂકી છે ને ખાસ ધ્યાન રાખજો. જો ધારો કે આ બ્રાઇટ ફ્રિંજ છે, આ ડાર્ક ફ્રિંજ છે ને આ બ્રાઇટ ફ્રિંજ છે. હવે હું તમને એવું કહું કે બે બ્રાઇટ ફ્રિંજ વચ્ચેનું ડિસ્ટન્સ ફાઇન્ડ આઉટ કરો. તમને ધારો કે સ્કેલ આપ્યો મેં હાથમાં, બરોબર છે, અને આવી રીતે મેં કહ્યું, તો તમે શું કરો, આ બ્રાઇટનું સેન્ટર ટુ આ બ્રાઇટનું સેન્ટર આપણે માપવું પડે, સેન્ટર ટુ સેન્ટર. અથવા તો કોઈ એવું કરે કે આ ફર્સ્ટ બ્રાઇટનું સ્ટાર્ટિંગ પોઈન્ટ અને સેકન્ડ બ્રાઇટનું સ્ટાર્ટિંગ પોઈન્ટ એ બે વચ્ચેનું ડિસ્ટન્સ ફાઇન્ડ આઉટ કરે. અથવા તો કોઈ એવું કરે કે ફર્સ્ટનું એન્ડિંગ પોઈન્ટ અને સેકન્ડ બ્રાઇટનું એન્ડિંગ પોઈન્ટ એની વચ્ચેનું ડિસ્ટન્સ ફાઇન્ડ આઉટ કરે. તો આફ્ટર ઓલ ઇટ વિલ ગીવ યુ ધ ડિસ્ટન્સ બિટવીન ધીસ ટુ બ્રાઇટ ફ્રિન્જીસ. પણ હવે જુઓ તમે કે જો આપણે ડિસ્ટન્સ બિટવીન ટુ કોન્ઝિક્યુટિવ બ્રાઇટ કે ડાર્ક ગમે તે લો, માનો કે તમે અહીંથી અહીં સુધી લીધું સ્ટાર્ટિંગ ટુ સ્ટાર્ટિંગ પોઈન્ટ, તો ડિસ્ટન્સ બિટવીન ટુ કોન્ઝિક્યુટિવ બ્રાઇટ ફ્રિન્જ એ જે આપણે ફાઇન્ડ આઉટ કરીએ છીએ ને, એની અંદર એક બ્રાઇટ અને એક ડાર્ક બે ફ્રિન્જ એકોમોડેટ થાય છે. એનો મતલબ કે distance between two consecutive bright fringes, that is the width of two fringe. એટલે જો ભૂલથી તમને એમસીક્યુમાં કે એક્ઝામ્પલમાં width of fringe find out કરવાની કહી હોય, તો પહેલા તમારે distance between consecutive fringe find out કરવાનું by this equation lambda capital D by small d, and then after divide it by 2 એટલે તમને width of one fringe મળે. ઇમ્પોર્ટન્ટ છે, ધ્યાન રાખજો આ વસ્તુ. ક્લિયર?